Good evening, everyone. Uh, I warmly welcome you all to today's webinar hosted by AI DataYard. To briefly introduce what it does, AI DataYard is basically Pakistan's first international e-learning platform that provides certified trainings and digital solutions for fields such as artificial intelligence, data science, machine learning, and so on. So thank you to everyone who has joined or is joining today, and hope you leave having learned something new today. So today's topic in discussion is federated learning and its applications. Federated learning basically enables mobile phones to collaboratively learn a shared prediction model while keeping all the training data on device without exchanging them. And simply put, it is a decentralized form of machine learning. And to elaborate this further, I'd like to invite our guest speaker, Ms. Farwa Khizar. So Ms. Farwa is working as a machine learning scientist at a Finland-based company called Comparables.ai. She also completed her master's in data science from FAST in 2021 with a distinction awarded with a gold medal. She has her research paper called A Payload Optimization Method for Federated Recommender Systems and accepted at REXIS 21 15th ACM Conference on Recommender Systems in collaboration with researchers from Finland. So, hi Farwa, how are you doing today?
Hi, I'm good. Thanks for such a nice introduction.
You're welcome. So shall we start?
Should we start it?
Yes, we can start.
Sure.
Sure.
So, hello. Hello everyone. It's me, Farwa, and I welcome all of you who has joined this webinar. And today, I will be talking about federated learning and its applications. Mahin, can you please let me know if my slides are shared with the audience?
Yes, they're visible.
Okay, that's great. So let's get started. So I hope by the end of this webinar, you will have a basic knowledge of federated learning, and you will have developed the interest, like what federated learning is, and what are its applications, and all that stuff. So let's get started. So the agendas of today's webinar is we will have an introduction to the federated learning, and we will see that how federated learning is different from state-of-the-art machine learning. And we will have some of the key concepts of the federated computation, and I will be covering some of the major applications of the federated learning, and then what are the active research areas in federated learning, and then last, we will be saying like what are the frameworks available for the federated learning. So federated learning is a machine learning that is based on decentralized data, and it has been introduced by Google in 2016. And it enables the edge devices to learn state-of-the-art machine learning models on decentralized data with privacy by default. Now, what is meant by this decentralized data? Decentralized data means that we have the data on multiple locations, on multiple sites, on multiple users' devices, or on multiple data centers, and the data is not accessible together at a single place to train state-of-the-art machine learning models. So federated learning aims to build a joint machine learning model based on the data that is located at multiple sites. So here, if we look at the figure, we have the federated learning server, and we can call this server as a coordinator. And it actually accelerates the training process of the federated learning. And initially, it holds a global model, and this is the model that we actually want to train on the data that is distributed across the devices. And then in each federated learning iteration, this server selects a chunk of federated learning users. In this case, you may assume it as mobile devices, users' phone devices, from a pool of users that are available for the training. And each of these users holds their locally stored private data. Now, what is meant by private data? Private data refers to the data that is sensitive or private as per related to the users or related to particular user. So each of the user holds their locally stored private data. And in each iteration, server sends this global model to each of the participating users, and users uses this global model to update their local models, and then this local model for the use to generate the recommendations and the model updates. And then these model updates are sent back to the server, and these are used by the server, and server actually aggregate these model updates, and then these aggregated updates are used to update the global model. And then this updated global model again sent back to another chunk or another pool of user participant in the next round of the federated learning. So this is an iterative process, and it actually continues until we reach the maximum number of iterations or we achieve the convergence criteria. So federated learning actually enables us to train machine learning models in a distributed environment without compromising data privacy and security. Now, how it's like provide us with data privacy and security mechanism, because we users have the data stored onto our devices, and we in federated learning we actually bring models to the data instead bringing data to the model. So it actually utilizes edge devices to learn a shared global model using local data and eliminates the need to move users' data to a central server. Now we will see that how federated learning is different from state-of-the-art traditional machine learning. So we might have an idea about traditional machine learning, how it works. So basically we have the central server and we have different data sources. And the idea is we collect the data from different data sources and store that data onto the data center on the central server. And then we further use this aggregated data or the collection of the data to train the machine learning models. As we know that data is increasing day by day, and we have the massive and huge amount of data. So we have already moved towards cloud infrastructures. Like we have been moved towards big data tools and technologies. And once the model gets trained on this large, massive amount of data, we make this model available to be used by the end users and the applications. Now, if you look at the whole architecture of traditional machine learning models, we users are required to send our data to the central server. Like our privacy is violated. So according to GDPR and other privacy rules, users might not be willing to share their personal and sensitive data to the central server or to the application providers, or companies itself might be less willing to record, upload, and store users' data onto the central server. So there are two major challenges that we face. Number one is the data privacy and security. And number two, we really need huge amount of data to machine learning models, especially when it comes to deep learning kind of models. So federated learning has several benefits over traditional machine learning. For example, it has a data privacy and its architecture is privacy by design. What does it mean? It means that we do not send our data to the central server. Instead, our data remains onto our devices. And that local data is being used to train the global model. Then we really do not need to worry about this handling of large data sets and handling and loading and storing and processing this large amount of data set onto the central server. Then we have real-time continuous learning. It's like that whenever we have the data available onto the devices and the devices are available for the training, we can train the models right after that. Like we do not need to wait for collecting the data and aggregating the data and storing them onto the data centers. And then after that, we should carry out the training. So another benefit is it has lower power consumption and minimal hardware, as we are not collecting huge data, so we have minimum hardware requirements. And usually federated learning is run on edge devices like mobile phones, so they really consume low power. So now I will be giving some of the key concepts of federated computation. We might have an idea about distributed data centers or distributed MapReduce. So basically, federated computation is next generation of that MapReduce. So assume here we in the figure we have clients, or you may assume that these clients are actually the mobile devices, and these mobile devices are recording the sensor readings or the temperature they have seen on a particular day, or the maximum temperature reading they have seen on the particular day. Now here comes the privacy technology one, which means on-device data sets. Which means that every of these devices is responsible for maintaining their own data. They are not required to exchange the data between them or between the server, and they are responsible for maintaining their own privacy. for updating it on daily basis. Like each of these devices should have the highest temperature they have seen on some particular day. And they should encrypt the data that's not in use or no longer in use. Okay, now let's formulate a problem. Let's say there is an engineer wants to answer key questions for this distributed data trainings. So let's assume that we want to know that what percentage of users or what percentage of users' devices have sensor readings greater than some certain threshold. So let's assume in this case we are setting this threshold as 60 degree Fahrenheit, and we want to know that what percentage of sensor readings are greater than the this 60 degree Fahrenheit temperature. So the first thing that the engineer would be doing is to impute the 60 degree Fahrenheit input as a threshold onto the server. And then server actually sends this threshold to each of the participating clients or the devices, and we name it as a federated broadcast, which means that whatever we have on the server, either it's model or whatsoever, we are actually broadcasting to each of the participants that we have in a particular training ground. And as a next step, devices take this threshold from the server, and they have their own locally stored data, which is the maximum temperature they have on that particular day. And then the idea is they will compute that local threshold with this threshold that has been given by the server. And they will see if their recorded temperature is greater than or less than that threshold. If it's greater, then it should be 1. If it's not greater, then it should be 0. And then devices actually broadcast the information in the form of 1 and 0. Now let's notice one thing here. We are not broadcasting the original data to the servers. Like the original data were there, we have the temperature readings. Now we are just sending the intermediate results. And in fact, these intermediate results are then aggregated by federated mean. So there comes another privacy technology too, which we name it as federated aggregation, which means that we are aggregating all the results that we have collected across the devices, and we are just persisting that aggregated mean onto the central server. So we are really not caring about what was original data of particular user or particular device. And server actually repeats this process for several times, for several iterations, because in each iteration, there is possibility that some of the devices are not available. And let's say we have some of the devices are available and they are participating in training, but unfortunately, due to some certain reasons, some of the devices got drop off. So this is an iterative process, and to get the better sense and the better results or sense of this problem answer to this question, this process should be repeated for a couple of iterations. So what's different from data center MapReduce? So whenever we talk about federated computations, their challenges are far beyond what we face in traditional data centers MapReduce. First thing is the limited communication. Federated learning training is usually carried out onto the mobile devices, and we already know that the mobile phones had limited communication bandwidth. And even they are connected to the home Wi-Fi networks, they have the limited communication bandwidth. Another is the intermittent compute node availability, which means that devices only participate in the training only if they are either they are on charging or they are connected to an unmetered network. And the third is intermittent data availability. So data onto the devices itself has the limited availability, and devices only participate as per the user permissions given by the user permissions. And then when we talk about the distribution of the data, then federated learning is much more massively distributed than traditional distributed data centers. So here is some of the sample magnitudes or roughly estimate, let's say, during the training or overall we have 1 billion of devices on which we want to take out or carry out the training process in federated learning environment. But out of 1 billion, we have just 10 million of devices available. And from that 10 million in each round, we are just selecting 1,000 of devices. And from 1,000, let's say 50 drop out due to some reasons. So the data is massively distributed when we compare federated learning with traditional data centers. Okay, so researchers and practitioners are actively applying federated learning in industry, and it has really promising applications in many industries in which data cannot be directly aggregated for training machine learning models due to factors such as intellectual property rights, privacy protection, and data security. So I will be covering some of the major applications of the federated learning. Number one is the mobile applications. Okay, so being a mobile user, it's really important for me. Either I want to share my personal data to the application providers or not. So federated learning has really empowered the mobile applications such as next keyword prediction, face detection, voice recognition by jointly learning the model on a large pool of devices. So later in the presentation, I will be covering a real use case of these mobile applications, that is Google Keyboard. Next, we have smart retail and the recommendations, and recommendations are everywhere. We are daily interacting with recommendations, and we are generating our user interaction behavior, user purchasing history, and all that stuff. Now, the traditional recommender systems requires us to record our user item interactions or user purchasing behavior or the history onto the central server. Only then they are capable machine learning models. But federated learning has introduced new ways to build recommender systems where we are no longer required to collect the user's data onto a central server to train these models. Third one, the most important one, is the smart healthcare, because we already know that the medical data such as disease symptoms or the gene sequences or the medical reports are really considered as the private and the sensitive data. And the medical data is really located in isolated medical centers, and medical institutions do not exchange this information with each other. So if all the medical institutions combine and unite and train a combined shared machine learning models based on federated learning, then I believe that it could greatly benefit to have to improve this smart healthcare system. Next major application is finance and banking. And the finance institutions really have very confidential and the private data. And finance institutions usually do not share their data across the other institutions. And due to this, currently the state-of-the-art machine learning models have the limited data availability for the finance and banking. So to create robust solutions for finance and banking, federated learning can really help, or even it's helping to have robust solutions for finance and banking by jointly learning the model based on the data that is located across the institutions. Now we have Internet of Things. Here I'm just going to explain about autonomous vehicles. So federated learning can greatly improve the self-driving car experience by real-time predictions and the data. And autonomous vehicles really need real-time information of the roads and the traffics. And I believe that federated learning can achieve all these objectives and improve this model by jointly learning based on the data across different vehicles. Now here comes a use case of Google GBoard. So Google has really practiced this onto their GBoard to improve the user experience. And the idea is, like, whenever we use GBoard, we come up with some of the suggestions. So either we click on the suggestions or not, the way we are interacting with the GBoard, all such information gets stored onto our devices locally. And then Google has actually built a federated learning system which actually uses this on devices local history of interaction of users with the keyboard, with the GBoard. And the next word prediction in GBoard keeps on improving based on not just a single single mobile phone, but it uses millions of devices to train the models. So as we know that devices only participate when they are idle or they are on charging to avoid any impact onto the mobile phone's performance. Okay, so next of the use case that I'm going to represent is one of the research that has been conducted by Huawei Helsinki Research Center. And they have actually, and it's related to recommendation systems, right? And they have actually extended the standard collaborative filtering to the federated mode. Might be some of you will have an idea of what standard collaborative filtering is, but on a brief note, standard collaborative filtering is like we have large user item interactions, like which items are liked by the user, or which items, or which user has rated which item. All such interactions sums up will creates a metrics that we call as a user item interaction metrics. We take these user item interaction metrics and decompose this large metrics into two small latent factor matrices, which we name as item factors and the user factors. And we train those item factors and the user factors. And at the end, when we have to make the predictions, we actually take the dot product of these two small latent factor matrices. And then this way, this collaborative filtering based on matrix factorization works. So now let's see that how they have actually extended that collaborative filtering to the federated mode. So on the server, we have a model Q, which we named as Q, and this is considered as a global model, and these are actually the item factors, right? These are the item factors are the global model because items are like the public information, which are accessible to every user. And then on every user devices, they have user interactions, user item interactions, and then they have their local model, which is actually the user factors. And in each iteration, server sends this Q model, which is item factors, to every participating users. And then users uses this Q model to update their local model, which is like user factors. Now, in order to update, and every user is responsible to update their local factors based on that item factor. But in order to update the item factors, we actually need the user factors of all the users. And in this federated setting, we cannot really exchange that user factors to the server, because these are really the information that we need to keep to ourselves. So update to the item factors cannot be done onto the user side. Instead, what they have proposed that we should calculate the gradients of the item factors and then send those gradients back to the server, and server uses those gradients to aggregate using a well-known famous stochastic gradient descent. So this was a very nice research, and very first, I believe, which has introduced that how can we actually achieve that standard collaborative filtering to the federated mode. So here I have given the link for that paper. You can go and check it out. So what are the active research areas in federated learning? Although we know that federated learning is privacy by design, but in every iteration, we could have some of the users who are actually the attackers, or who could be the malicious users. And the model updates sent by those users could actually leak some of the important parameters that could actually breach the user data privacy or security. So, and due to these attacks, malicious servers can have an idea like what kind of data that has been used during the training process. So researchers and practitioners are applying some of the state-of-the-art privacy mechanisms to the federated learning. And here I have listed three of them: differential privacy, homomorphic encryption, and secure multi-party computations. These mechanisms have been already used for state-of-the-art machine learning models to make them secure and private. But now the researchers are trying to enhance the security of the federated learning by employing these different techniques. So differential privacy is a very common technique. What we actually do with this, we add noise to the input or the intermediate results before sending them to the server or whatsoever. So that reverse engineering the data becomes hard. And as we are adding noise to the data, so we might expect decrease in the accuracy. So it actually involves a trade-off between the accuracy and the privacy. Then we have homomorphic encryption, which actually protects the data privacy through parameter exchange using some secure encryption mechanism. And unlike differential privacy, it doesn't exchange or transmit the data or the model. Then we have secure multi-party computations, which naturally involves multiple parties and provide us well-defined simulated framework to have complete zero knowledge, and each party knows nothing except its input and output. So another active area of research in federated learning is payload optimization. And I will be actually elaborating what is this payload optimization by linking this problem to the FCF paper that we have seen before that were based on recommender systems. So it's normal that whenever we want to achieve the model conversions, FCF and other similar recommender systems requires several communication rounds between the server and the user. And the computational payload, which is also known as the carrying capacity of a packet or transmission data unit that we send across or between the server and the user, it directly depends on the size of the global model. And if you remember in the previous slide, we have seen that the Q model is the item factors, and the size of the global model here is like number of items into the number of factors. So this model payload increases linearly with the increase in the number of items. So here in the table, I have demonstrated that let's say we have recommender systems that have items ranging from 3,000 to 10 million, then this payload can approximately exceed 1 GB, which is quite huge. And recommender systems with million of items in production, it really becomes challenging, not only for the users, but also for the broadband and mobile internet service providers and operators. So this is another problem that has been researchers are working on. Me myself has also worked on this problem along with researchers from Huawei Helsinki Research Center, and we have actually formulated a solution to tackle this problem, and we devised a solution that is actually based on multi-armed bin data classical approach to reinforcement learning. So the idea that we have used is like instead of transmitting the full global model in each iteration to every participating user, it is better to just send a part of the global model to every participating user. And we have really decreased this 100% payload from 100% to 10%, which means now we are just using 10% of the payload in every iteration, and users are using just that 10% of the payload to train their models. And even though we have achieved more or less the same recommendation performance as compared to the FCF. So I have also given the link for this paper. You can go and read it out. I hope you would like it. And if you think that this problem is interesting, then you must give it a read. So what are the federated learning frameworks that we are available these days? So we have fast-growing open source projects for federated learning, especially when we talk about TensorFlow Federated, which is actually introduced by Google again. So it's an open source framework for experimenting with federated machine learning and other computations on decentralized dataset. And then we have PySwift, which is actually a Python library that provides federated learning framework for building secure and scalable machine learning models. And we have a couple of other frameworks and the libraries. You can go and check it out, and you can get started with these libraries to simulate the. So now we are at the conclusion. So we know that data security and the privacy is one of the major concerns for every user. The traditional and state-of-the-art machine learning models requires their data onto the central server, which is like violating the user data privacy and security. And federated learning has give us new ways to build robust machine learning solutions or machine learning models while keeping data onto the devices and training the machine learning models in a distributed environment without compromising data privacy and security. And we can learn a shared global model using local data, and it really eliminates the need to move the user data to a central server. So here I have given a couple of references which you can go and read. And if you think that you want to work with federated learning, then you should go and read these articles. And these articles have deep dive or some of key concepts that or the work that people are really working on federated learning. So I would recommend to go and check out these papers. At the end, I would like to thank everyone who has joined me and who has joined this webinar. I hope you might have get some of the idea of federated learning, and if you want to kickstart with the federated learning, or if you want to start working on federated learning, then I believe that you can do that. So thank you, everyone. And last, I want to thank AI DataYard for having or conducting this webinar. So thanks for everyone.
Okay, thank you so much, ma'am, Farwa, Khizar. So we'll take some questions at the end
Sure.
from the viewers. Okay, we have this question. We have
Okay,
this
the
question
question
from
is
the
why don't we use our own data server or data center for healthcare and finance? Okay, the problem is the finance or the health data is actually distributed across the devices. And I believe that sharing this data is really difficult, and collecting and storing this data is difficult, because if you even talk about the financial data is very confidential. I don't think if we can really exchange this data across the devices. Finance data contains the data of the customers, and the customers data is again violating the users data privacy or something like that. So traditionally, what we are doing right now, we are doing the same thing. We are maintaining our data servers, but the main challenge is we are like facing is like we have the limited availability for these kind of data sets. So I think Federated Learning provides that platform where we do not need to worry about maintaining those data centers, collecting those data to the data centers, and so on.
Okay, our next question is by Mohammed Umair.
Okay, what about the latency issues? And with very low power devices like smartwatches data, yes, we can have the latency issues with the federated learning, but again, as I mentioned earlier, that we could have some of the devices that drop off due to some certain reasons. So the reasons revolve around all these issues. So when we do continuous training or iterative process training, then we have the chances that we could have that device again in the training process, and with some troubleshoot latency issues. So yeah, you are right. There is a latency issue. There could be a latency issue. Thank you.
Okay, are there any more questions? If so, you can type in the comments. We'll put them.
So we do not have any other questions.
I do not think we have any more questions. Okay. So
Okay.
thank you so much. I genuinely learned a lot, even though this isn't
Thank you.
exactly my field, but it was
Okay.
actually very informational, and I learned
Okay,
more
here
than I
we
knew.
have another
Yeah.
question. Here we have
Okay,
another
we can.
question. How can we protect data poisoning attacks in federated learning? Yes, that's the same thing that I was previously referring to, enhancement of the data security or the model security. So the security mechanism that I have shown, differential privacy, homomorphic encryptions, can help us to enhance to avoid these poisoning attacks. So solution is like we can use those mechanisms to avoid these attacks.
Okay,
Can you
Muhammad
please
Umair is
share the
asking to
slides?
share
And okay,
slides.
sure.
Sure, we share them.
You're welcome.
Okay, thank you so much. I genuinely learned a lot. Thank you for. I
Thank
would
you.
like to thank Ma'am Farwa Khizar for joining us today, especially, and also AI DataYard for putting up this webinar. So we also thank you all, the audience, for joining this webinar today. And you have to make sure to follow AI Data Yard on different platforms to also keep up to date with any upcoming webinars we may have. And till then, we are going to sign off. This is Mahin, and my guest is Miss Farwa.
Thank
Khuda
you.
Hafiz.
Thank you. Bye, everyone.